base impedance, or resistance into the base of a transistor. How can we go about determining what this is? If we take a look at a very simple model here of a transistor, and we notice that we have the voltage at the base, and that happens to be equal to the voltage base to emitter. And we have a current going into it. Now, by definition, impedance or resistance, impedance is actually a complex resistance. Impedance is equal to the ratio of the voltage to the current. So we can say that Z, or the impedance into the base, is equal to the voltage at the base divided by the base current. This is simply Ohm's law. And of course, in our case, in this particular example, the base impedance is equal to voltage base to emitter divided by the base current. Now the question arises, what happens to this impedance if we add a resistor in the emitter path? Well, we're just going to try that and see what happens. We'll just add an RE, and everything else remains the same. We have a voltage at the base, we have a current going into the base, we still have a voltage base to emitter, and now we're going to apply exactly the same principle. So what is the voltage at the base? Well, the voltage at the base, according to Kirchhoff's voltage law, is equal to the voltage base to emitter plus the drop across RE. That happens to be the emitter current, IE, times RE. Now, we'd like to write this in terms of base currents. And so we recognize that IE is actually made up of two components. And those are IC plus IB. So this is an equally true statement. We also recognize now that IC is related to IB by means of beta. So we can write that voltage in the base is equal to VBE plus, and it will be beta times IE plus IB times RE. So now we can factor out the IB out of here, and that gives us beta plus 1 times IB RE. So now we kind of have an expression for voltage in the base, and we're going to now plug that into here, divide by IB, and see what we get for impedance in the base. The impedance in the base now becomes this VBE plus beta plus 1 IB RE, all divided by IB. So this can be simplified to simply VBE divided by AB. And notice that happens to be the original impedance that we saw looking into the transistor. Plus, and notice here the IBs will cancel out, and we're left with beta plus 1 times RE. So notice that the impedance looking into the base has increased by this amount. Now, most textbooks at this point will come along and simply state, we can sort of forget this, the original input impedance, because it's relatively small compared to beta times RE. So most textbooks will simply say, since VBE divided by IB is much, much less than beta plus 1 times RE, ignore it. And they make the second assumption that since beta is much, much greater than 1, ignore the 1. And so you'll notice that most textbooks will say that the input impedance is approximately equal to simply beta times the emitter resistance. And this approximation is easy to remember, and will get you very close to the actual input impedance. The real number will actually be higher than this, but it doesn't matter. If the number was lower than this, that might be a problem, but since the real number is going to actually be slightly higher, this simple rule of thumb works quite well.